Okay, today we are going to study about the chapter first, Statistics in Engineering. Did you download the class material? Okay. And this is the chapter outline. Firstly, we are going to study about the engineering method and the statistical thinking. And we are going to study about the collecting method of the engineering data based on the basic principles and the observational study and the designed example, experiment, and the observed processes over time. And after finishing this chapter, we are going to study about the mechanistic and the empirical models. And this is the learning objectives for the chapter first. After careful study of this chapter, you should be able to do the following. First, you can identify the role that statistics can play in the problem-solving process for engineers. And then you can discuss how the variability affects the data used for engineering decisions. And then you can explain the difference between enumerative study and the analytical study. And then you can discuss the different methods that engineers use to collect data. And then you can identify the advantages that the designed experiments have in comparison to the other method of collecting engineering data, such as the observational study, as I mentioned in the previous slide. And then you can explain the differences between the mechanistic model and the empirical models. And firstly, what do engineers do? An engineer is someone who solves the problems of interest to society with the efficient application of scientific principles by refining existing product, 기존에 존재하고 있는 제품을 개선하는 것, and designing new product or processes. So this is the creative process, and this is the sequence of the engineering method. Firstly, we have to develop a clear description on the problem. That's the first step. And then we have to identify the important factors affecting the problem. And based on these important factors that we selected, we can propose or refine the model. And we have to conduct experiment to verify the proposed or refined model in previous step. And normally these three steps are required to have the multiple iterations to obtain the final solution. That we have to manipulate the model, and we can confirm the solution based on this model by performing the additional experiment. And after the confirmation, we can draw the conclusions and recommendations. That is how we can have the engineering method. And this is the general sequence of the engineering method to create some product. And the statistics normally support the creative process. And the field of statistics and use of data to make decisions and to solve problems and to design products and processes. Because many engineering practices involve working with the data, obviously some knowledge of the statistics is very important to any engineers, such as architectural engineers and the chemical engineers and civil engineers and etc. Normally the experiments and processes are not deterministic, which means that we are not 100% sure that the conclusion from the experiment or the product from the processes are obtained as we expected. So the statistical techniques are useful for describing and understanding the variability. And by the variability, it can be noted that the successive observations of a system or phenomenon do not produce exactly the same result. This means that even though we provide the same procedure of the engineering method, the conclusions can be different. So we have to always think about the variability. And the statistics gives us a framework for describing this variability and for learning about the potential sources of the variability. And this is the first example for the variability. And an engineer is designing a nylon connector to be used in an automotive engine application. And the engineer is considering establishing the design specification on wall thickness at 3 divided by 5 inches, but somewhat uncertain is about the effect of this decision on the connector pull-off force. If the pull-off force of this nylon connector is too low, the connector may fail when it is installed in an engine. And this causes some problem. So we have to find the optimum wall thickness of the nylon connector to resist the applied pull-off force. So the 8 prototype units are produced and their pull-off forces measured are as follows: 12.6 pound and 12.9 pound and 13.4 pound and 12.3 pound and 13.6 pound and 13.5 pound and 12.6 pound and finally the 13.1 pound. And the dot diagram is a very useful plot for displaying a small body of data. For example, if the number of obtained data is below 20 observations, we can very effectively use this dot diagram. And this plot allows us to easily see 2 features of the data. First one is the location of the data, and the second one is the scatterness or variability of the data. And this is a typical example of the dot diagram for the pull-off force data when the wall thickness was 3 divided by 3 inches. And this dot indicates each data point obtained from the experiment. And based on that, we can easily determine the average value. The average value is about 13.0 pounds. And we also can see the scatterness of the data, how the data are scattered based on this dot diagram. And if we assume that the pull-off force should be higher than the 13.5 pounds to resist the pull-off failure, we can easily determine based on this dot diagram whether these data are enough to resist the pull-off force or not. So this is very effective method to evaluate the data when the data point was lower than 20 observations. If 13.0 pound, which is the average value of the pull-off force for the nylon connector with the wall thickness of 3 divided by 3 inches, is insufficient to resist the pull-off force, the external load, the engineer should consider an alternative design because we cannot use this nylon connector in an engine. So we're selecting a new 8 prototypes, and the pull-off force of these 8 prototypes are measured. And the dot diagram can be used to simply compare 2 sets of data. And this is the typical example for the dot diagram of the pull-off force for two wall thicknesses. And the dot with blue color indicate the nylon connector with the wall thickness of 3 divided by 32 inches. And the circle indicate the new nylon connector with the wall thickness of 1 divided by 8 inches. So, as you see here, by increasing the wall thickness from 3 divided by 32 inches to 1 divided by 8 inches, we can easily see that the average value of the pull-off force for the nylon connector with the higher wall thickness exhibits the higher value. Why? Because the average point of this circle is about 13.4 pounds. So, by using the dot diagram, we can easily compare the performance of the two sets of data, as you can see here. So we can determine which one gives the better performance. But as you can see here, the scatterness of the data obtained from the nylon connector with the higher wall thickness is very similar to that obtained from the nylon connector with smaller wall thickness, which means that scatterness of the data is not affected by wall thickness. So we can evaluate two important things from this dot diagram. The average value of the pull-off force for each nylon connector and the effect of wall thickness on the scatterness data. Okay? So this is very useful method for comparing the performance of the data point obtained from two different sets when the number of data points is below 20 observations. Since the pull-off force varies or exhibits variability, it is called a random variable, which is called 확률 변수 in Korean. And a random variable x can be modeled by this equation. X equals to the summation of mu and the epsilon. And mu indicate the constant value, and epsilon indicate the random disturbance. In real situation, the epsilon never equals to 0, which means that the random variable always exhibits the variability. And now we are going to think about the ways to reason. Reasoning means 추론 in Korean. And there are two ways for reasoning, for doing the reasoning. First one is that we can design the product based on the physical law. For example, we all know about the Ohm's law. The current equals to the ratio of voltage and resistance. And based on this physical law, we can simply design the electric wire, 전선, for example. So we can design the product based on the well-known physical law. This is the one way to obtain the reasoning of regarding the statistics. And there is also another way to obtain the reasoning from the statistics. And this is another example. And based on the small sample of people, and by evaluating the sample of people, we can presume the performance or characteristics of the whole population based on statistical inference. 통계적 추론. So as you can see here, we can presume the performance or characteristics of the population from the previous small sample of people there will be a sampling error always. So if we select properly the sample of people, we can significantly reduce the sampling error from this method. So it is very important to collect the data for presume or predict some performance or characteristics of the total population. This is the method of the statistical inference. So, as I mentioned previously, the collecting data is very important part for the statistical inference. We have three basic methods for collecting data. The first one is the retrospective study using historical data. And in the case, the data is collected in the past for other purposes. We can use the data which was collected in the past for the other purposes. So we can have a lot of data, but there is little useful information. Okay? And the second method is the observational study. And in this case, we can obtain the data which was presently collected by a passive observer. And it is conducted for a relative short time period. The variables that are not routinely measured can be included. So the data point obtained from this method can be out of bounds regarding the subject of the experiment that we are currently interested in. So that means we cannot use all the data from this method. And the third one is the designed experiment. And this method can lead to deliberate or possibly changes in variables. And the data which is collected in response to process input can be also changed according to the experimenter. So this is the most effective way to collect the data regarding the engineering science. So we are going to briefly explain about this method. And this is the typical example for this designed experiment, which is called the factor experimental example. And we can consider a distillation column. And this is the test setup for the distillation column. And this is the lamp distillation flask here. And there is a mixture of acetone and water. And there is a thermometer to measure the temperature inside the flask. And the evaporated mixture is going through this cooling system, and the evaporated mixture finally condensed to the solution by passing this cooling system. And the cold water can be included in this part and going through this cooling system, and the water is getting out here. So normally, the boiling temperature of the acetone is lower than that of water. That means if we can control the boiling temperature, we can only obtain the evaporated acetone, right, from this experiment. And the evaporated acetone can be condensed by going through this cooling system, and then we can finally obtain the condensed acetone again here. That is the solution. But sometimes the water is chemically included in the evaporated acetone. So the concentration of the acetone here is not 100%. So if we repeat this process as much as we can increase the concentration of the acetone, right? So we can call this is the reflux. So based on this experimental setup, we can simply think that the output is acetone concentration. And what is the input? Inputs are the reboil temperature, the boiling temperature, and the condensate temperature, the temperature of the cooling system, and also the reflux rate. How many times you repeat the experiment? And based on these three steps, we can change the concentration of the acetone, right? So the output changes as the input are changed by the experimenter. So how many outputs can be obtained by this system? If we assume that each factor is set at two reasonable levels, -1 and +1, and -1 indicate the low something, and +1 indicate high something, we can effectively use this level because this makes sense that the low reboil temperature and high reboil temperature, we can simply apply these two steps. And also, we can have low condensate temperature and high condensate temperature. Also, we can have low reflux rate and high reflux rate. So, if we have the two reasonable levels based on these three inputs, we can finally obtain 8 outcomes. Why? We have two different levels for the reboil temperature. High reboil temperature and low reboil temperature. And in the case of high reboil temperature, we also can have two different condensate temperature here. The condensate temperature will be +1 high or -1, right? And this system can also be applied to the -1 reboil temperature as well. So we can have also +1 and -1 here. And we have one more input, which is called reflux rate. And in this case, we have also two different levels, -1 and +1. And if we think about the high condensate temperature, we can have two reflux rate, +1 and -1, right? And we can apply these things to here, here, and here, right? So we can finally have total 8 outcomes based on this system. So how can we simply calculate the number of outputs based on this factorial experimental setup? We have two reasonable levels and three inputs. So we can simply have the sum of 2. This is the number of levels, and this is the output. So we can obtain 8. So the 8 runs are made at every combination of factors to observe acetone output. And it allows one to detect the interaction between factors. And this is the table for the designed experiment factorial design for the distillation column. And as you can see here, this table is exactly the same with this flow chart. Rather than using this table, you can make this flow chart, or you can calculate the number of outputs by using this equation. It's much easier to draw the conclusions. And also, we can think about the coordination system. We have 3 inputs First one is the reflux rate, and the second one is the revolve temperature, and the third one is condensate temperature. And each input, we have two options. First one is the low something, the other one is high something. So based on this coordination system, we can simply make this cube hexahedron system. For example, this edge point indicates the case with low revolve temperature, -1 here, and the low reflux rate here, and the low condensate temperature here. And what about this point? This point indicates the case with low revolve temperature and the high reflux rate and low condensate temperature. So this coordination system can be simply changed to the cube hexahedron description here. Now, we are going to consider a new design of the distillation column. And if we design the new distillation column, when we design the new distillation column, if we make this new system as similar to that of the old distillation column, we just can have one more input. That is the new system, the new design of the distillation column. Why? Because the newly designed distillation column has the same test setup with the old one, and it also has the same input: revolve temperature, condensate temperature, and the reflux rate. So we just can think this as a new input from the system to the system. Okay? Because this distillation column has the same system with the old one. So in this case, we increase the number of inputs from 3 to 4, right? So how can we calculate the number of outcomes? Is that the first power of 2, okay? Because now we have total 4 inputs. First one is the revolve temperature, second one is the condensate temperature, third one is the reflux rate, and the last one is the new system. So if you calculate this one, that is 16. So the response of the old and new designs can now be compared, and the most desirable process and its settings are now selected as optimal. So this is the coordination system also, and we have the same coordination system with the old distillation column system, because these two column designs have the same inputs. So based on this coordination system, we know how to make this cube hexahedron description, right? And this edge point indicates the case with the low revolve temperature, low reflux rate, and low condensate temperature. Since the new distillation column has the same system with the old one, we can have the same cube hexahedron description as well, based on this coordination. So we have total have the 16 edge point, okay? But this type of factorial experiment can easily get too large. For example, if we consider just 8 inputs, we require the 8 power of 2 equals the 256 experimental runs of the distillation columns are required. That is too much. We never can perform 200 experiments So the certain combinations of the factor levels can be deleted from the experiment without degrading the resultant model. And I'm going to explain how this is working. And the result from this process is called a fractional factorial experiment. And this is a typical example. Since the old distillation column has the same system with the new distillation column, we can reduce some inputs because, for example, if we have just these 4 cases from the old distillation column system, we can simply expect that the result from these 4 points can be also obtained from the new system. Because the new distillation column has the same system with nothing is changing, but just we add the new distillation column. So in this case, the old distillation column and the new distillation column experiment have the same system. We can reduce the 50% of the experimental noise. Okay? Because if we measure only the column, point from the new distillation column, because the inputs are exactly the same. Do you understand? So, based on these 2 things, we can reduce the total number of runs from 16 to 8. Now, we are going to think about the 30 distillation column runs. Whenever the data are collected over time, it is important to plot the data versus time. And the phenomenon that might affect the system or process often become more visible in a data-oriented plot. And this is the typical example of the dot diagram for these 30 distillation column runs. And as you can see here, it is quite difficult to find the average value from this dot diagram. And it is difficult to determine whether or not the data points are too much scattered, because the data points are too much for this dot diagram. So, in this case, we are not using the dot diagram, but instead, we can use the time-oriented curve as shown in here. Because just we have 1 or 2 distillation column experiment, right? Based on the previous slide, we have just old one and the new one. And if we want to measure the acetone concentration, we can obtain this data point and this data point at the different time. Because just we have 2 old and new distillation column experimental system. So each data point for the acetone concentration is based on the orientation number or the time. So we can draw acetone concentration as a y-axis, and we can draw the time as the x-axis. And as you can see here, the acetone concentration is getting slightly increased with the observation number, but it is going down after some certain point. So we can simply presume that, there is something is wrong here, because the acetone concentration is getting down somehow. So we can change the experimental setup, or we can improve the experimental setup to obtain more consistent values. W. Edward Deming, who is a famous industrial statistician, conducted an illustrative experiment on process over control or tampering. And let's look at his apparatus and experimental procedure. And based on his experimental setup, the marbles here were dropped throughout the funnel. This is the funnel here. Onto a target. This is the target. And the location where the marble struck the target was recorded. So we can measure the distance between the striking point of the marble to the center of the target. So we measure the distance. And the variation was caused by several factors in this experiment. Firstly, the marble placement in funnel and release dynamics. How we can release the marble? That definitely location of the striking point of the marble after going through this funnel. And also the vibration of the funnel. And the vibration of the funnel will cause the different striking point of the marble, right? And also the air current and the measurement errors. And from these things, sometimes normally we have the variation, which means that the striking point of the marble is not always corresponding to the center of the target. Okay? There is some distance between the striking point and the center of the target, even though we adjust the funnel to the center of the target. Okay? And the funnel is aligned with the center of the target, and the marbles were dropped. And the distance from the striking point to the target center was measured and recorded. And there are two strategies. First one is that the funnel was not moved. And then the dropping the marble is repeated. That is the strategy one. And the strategy two is that the funnel was moved on equal distance in opposite direction to compensate for the error. Then the process was repeated. And as I mentioned previously, we cannot obtain the zero distance from the striking point of the marble to the center of the target normally. And in that case, if we drop the marble throughout the funnel, we can measure the distance, right? So if we assume that this is the target, and this is the center, and this is the striking point of the marble, we can simply think that this is the plus direction and this is the minus direction. In that case, we have plus distance, right, from the striking point of the marble to the center of the target. And to reduce or to compensate this error, how can we do? We can change the point or the location of the funnel to left side, right? And we move the funnel to the left side, we probably obtain the minus distance. And we can change the funnel direction to the opposite side, but the distance is same. And we can repeat this process, right, to reduce the error. That is the strategy 2, okay? The strategy 1 is that the funnel was not moved, but in the case of the strategy 2, the funnel was moved in the opposite direction with the same distance. And this is called adjustment. And this is the test result. and the light blue color indicate the case with adjustment, which is the strategy 2. And the dark without adjustment, this is the strategy 1. And even though we apply the strategy 2 to reduce the error, as you can see, we have more variation. And as you can see, the approximately 2 times larger variation was obtained in the case with the adjustment. So this case, we can simply say that the adjustment were overcontrolled. 너무 과하게 조절이 됐다. And the process and the increases the deviations from the target, which means that based on this test result, we can simply think that the funnel should not be moved during the test, okay, based on this test result. So applying the too much adjustment causes some more error from the data point after experiment. And this is the simple conclusions from the Deming's experiment. And the lesson of the Deming experiment is that the process should not be adjusted because it increases the variability in response to random variation. But only when a clear shift in the process value becomes apparent, then a process adjustment should be made to return the process output to their normal values. And I will explain this here. We can drop the marble several times, and we always obtain the plus distance. In that case, we can think that this direction or the place of the funnel is not appropriate for this experiment, right? After several testing. And in the case, we can adjust the distance, the direction of the funnel to be more centered, to be closer to the center of the target. And then we don't have to move the location of the funnel, and then we can repeat the test again. Okay? This is exactly different with the strategy 2. Strategy 2, we have to move the location of funnel every time. But in this case, we just move the funnel one time based on the previous data point that we obtained. Okay? So this will be explained in the later slide again. So to identify when the shift occurs, we can use the control chart. And I will explain what is the control chart. And this is the typical example. And the dark blue color line indicates the case without adjustment. And at the very beginning, we have very nice data point. Even though there is a variation, the average value is very close to the center. This is the center of the target. But as you can see, after a certain point here, probably here, the data point is going up somehow, right? Even though, so we can simply think that from this point, the experimental setup has some problem. So as I mentioned previously, by using this diagram, we have to move or adjust the location of the funnel to obtain more data closer to the center of the target. So if we adjust the direction of the funnel at this point one time, we can clearly obtain the data point closer to the center of the target, even though the variation is identical with the previous one. And when to apply this adjustment or by what amount. The control chart is normally used for deciding when we have to apply the adjustment or what amount. And its characteristics are time-oriented horizontal axis, normally hours or days or minutes. And it also has the variable of interest vertical axis, such as the percentage of the acetone. And we can use the long-term average as a center line. And we can use the long-term used variability as an upper and the lower control limit around the long-term average. So that means we can measure the data point as much as we can, and based on the data point, we can have the average value, right? So we can have the average value as the center line, and then based on the long-term data point, we can have the variability, right? And based on that variability, we can decide the upper and lower control limit. And if the data point obtained exceed the upper or lower control limit, we can think that this data point has some problem. So we have to delete that data point, or we have to adjust the experimental setup. Then the data points are plotted over time. If the plot points are between the control limit, then the process is normal. If not, it needs to be adjusted. So this is the typical example for the control chart. And as you can see, this is the average value obtained from the numerous data points. And this is the upper control limit, and this is the lower control limit based on the variability of the previously measured the numerous data point. And the upper control limit is 3 multiplied by the standard deviation. And the lower control limit is the 3 multiplied by the standard deviation. And as you can see here, at the first, we can have very good data points. And those data points are closer to the average value, and there is no data exceeding the upper or lower control limit. But as you can see, when the observation number is getting increased, we have some point exceeding the lower control limit, which means that this data point should not be used, or we have to adjust the experimental setup from this point. So this is the control chart, and based on this control chart, we can evaluate the quality of the data point. And now we are going to talk about the 2 different methods for the control chart. One is the enumerative studies, and in that case, we can use the control chart made from random selecting some samples from a lot. For example, we can sample and measure the resistivity on 3 semiconductor wafers, 반도체 in Korean, selected from a lot, and use this to evaluate the lot. And there is also another method which is called analytical studies. And this study, we can have the real-time control over production process. For example, we can use data from current production to evaluate the future production. And I will explain these 2 different methods by using these figures. And the left side indicates the enumerative study. And as you can see here, we can simply select some samples from the population. And by evaluating the performance of the selected sample, we can simply presume the performance of the whole population, right? That is how the enumerative study is working. And in the case of the analytical study, we can select some samples from the current product and evaluate the performance of the selected samples. And based on the evaluation, we can predict the performance of the future population by assuming that the production process is identical, it's not changed. So the analytical study is considering the time, which means that we can have some samples from the current product, and based on their performance, we can predict the performance of the future production. Okay? By assuming that the production process is not changed. So you now can differentiate the enumerative study and the analytical study. Okay? Now, we are going to talk about the mechanistic model, and which is built from our underlying knowledge of the basic physical mechanisms that related to several variables. For example, as I mentioned previously, we can think about the Ohm's law. And Ohm's law is that the current equals to the voltage divided by the resistance. And we can simply present this as this equation, I equals to E divided by R. But the current is affected by several things. For example, the vibration of the electric wires and the size of the wires and the relative humidity and etc. That means even though we can use this equation, we cannot obtain the exact value of the current. So we always have to considering about the variability. And in this case, we can simply provide the summation of epsilon for taking into account the variability of current by several factors. So the mechanistic model, as you can see here, is based on the physical law and the physical mechanism or mathematical knowledge. But there is also an empirical model, and this is built from our engineering and scientific knowledge of the phenomenon, but it is not directly developed from our theoretical or first principles by understanding the underlying mechanisms. For example, in the case of the concrete, we produce the concrete by including 4 different components. First one is the cement, the second one is the water, and third one is the coarse aggregate like gravel, and the fourth one is the sand, fine aggregate. So since the concrete is consisting of these 4 different materials, it is really difficult to predict the strength of the concrete. It is almost impossible. So how the engineers are doing is that they normally gathered a numerous data point obtained from different researchers, and they make a relationship between the strength with other factors, such as the ratio of water and cement, or the amount of coarse aggregate, or the amount of sand, and etc. So based on the data point, they can simply presume the equation based on the regression analysis, 회귀 분석 in Korean. 그러니까 회귀 분석을 통해서 보통 도출해요. So this is a typical example for the empirical model. And in the architectural engineering field, we normally use the empirical model rather than the mechanistic model because there are so many uncertainties affecting the result of some performance of the construction materials or the structures. So this is the typical example for the empirical model. We are interested in the average molecular weight, Mn, of a polymer. Now we know that Mn is related to the viscosity of the material, V, and it also depends on the amount of catalyst, C, and the temperature in the polymerization reactor when the material is manufactured. So the relationship between the molecular weight, Mn, and these variables is Mn equals to the function of VCT. And in that case, we don't know about the form of the function f, right? And we can estimate the model from the experimental data to be of the following form where the betas are unknown parameters. And for example, if we simply assume that the relationship between the molecular weight and the viscosity of the material and the amount of catalyst and temperature is the linear relationship, we can simply predict this formulation. This is the linear formulation. 1차 함수잖아요, 선영. So, Mn equals to the summation of beta 0. Beta indicate the coefficient. Beta 0 plus beta 1 multiplied by V plus beta 2 multiplied by C plus beta 3 multiplied by T plus epsilon. And based on the data point, we can find the coefficient based on the regression analysis. Okay? And this is the different example. Finished semiconductor is wire bonded to a frame. In an observational study, the variables recorded were the pull-out strength to break the bond, which is called Y, and the wire length, which is called X1, and die height, which is called X2. Unfortunately, there is no physical mechanisms that we can easily apply. So in this case, we have to use the empirical model. And the data recorded are shown on the next slide here. And this is the data point obtained from the experiment. And this is the observational number. And this is the pull-off strength. This is the wire length. And this is the die height. And based on this data point, we can simply assume that the pull-off strength has a linear relationship with the wire length and die height. And by this assumption, we can simply have this equation. In this case, we don't know about the beta 0, beta 1, beta 2 yet. In general, this type of empirical model is called a regression model. 회귀 분석, 회귀 model. And the estimated regression relationship is given by this equation. And that means that based on the previous data point, we can obtain this final equation. The pull-off strength equals to 2.26 plus 2.74 multiplied by the wire length plus 0.0125 multiplied by the die height. And the regression model is called a method of least squares. And the method of least squares chooses the parameters in the empirical model to minimize the sum of the square distances between each point and the line represented by the model equation. And we can simply use this equation. This is the summation, right? And if we assume that this is the data point, So what is the least square error method? Which is that we are trying to find the minimum value of the least square distance between the data point and the point obtained from the equation or model. Okay? So this is the function that is obtained or determined from the least square error method. So this is the least square error method. Okay? So by using this formulation, we can find the optimum, the coefficient from the assumed model. Do you understand? So this coefficient was obtained from this formulation. So this is the data point, and the y-axis indicates the pole of strength, and x-axis indicate the wire length, and the z-axis indicate die height. And as you can see here, the pole of force, pole of strength clearly increases with increasing the wire length, right? If you increase the wire length, the pole of force is also increased. The pole of strength is not affected by the die height. As you can see, there is no variation of the pole of strength according to the z-axis. And based on the least square error method, we can obtain this optimum plane here. And this is the plane providing the minimum value of this equation. Okay? So this, as you can see, this is very similar to the data point. And this is end of today's class. See you on Friday.